Okay, so I said I was going to talk about a special case of the inverting amplifier topology, and I figured out that that special case is actually a special case for the non-inverting amplifier topology. So I moved it in my slides, and so now my slides are going to be out of order. But I think that that's okay. I'd rather keep the videos in order than the slides in order. So we'll get to that one after we do the non-inverting amplifier topology. But now let's go ahead and do the same kind of analysis that we did previously, where we're going to go ahead and derive the expression for this non-inverting amplifier topology. You notice that the difference really is that we took this input, which was previously over here, and this was grounded. And now we're grounding this minus input, and we're sending the input signal to the plus terminal instead. The feedback network looks exactly the same. We've just taken the input and we've moved it from the minus terminal to the plus terminal. So that's how you can distinguish the non-inverting from the inverting amplifier topology. Really, the feedback network of the resistors is going to be exactly the same. It's just a matter of where my input signal is. If my input signal is going to the plus terminal, then I'm on the non-inverting amplifier topology. If it's going to the minus terminal, then I'm on the inverting. In that case, I'd be on the inverting amplifier topology, okay? That's important. Hopefully that makes sense. I know I've been calling these the plus and minus terminals thus far. Better names for them really is that this is called the non-inverting terminal, and this is called the inverting terminal. Okay, so if you rather call them by those names, then feel free to do so. But let's go ahead and do a similar analysis to what we did previously. Obviously, we have a voltage source here. Let's go ahead and just make it clear that all of this, this entire node is grounded. So this is all 0 volts here, 0 volts, right? And since we have a voltage source here, we're going to end up with a voltage of VI at the plus terminal. And again, we're going to invoke our golden rule. And so that means I'm going to end up with VI at the minus terminal as well, because the voltage at the two input terminals has to be the same. Let's recall also that there will be no current flowing into the op amp. So in this case, again, I1 is going to be equal to I2. All the current that flows here is going to flow here. None of it will go this way, okay? So knowing that, let's go ahead and write these expressions for I1 and I2 again. We know that I1 is going to be equal to I2 ultimately. So let's just write an expression for I1. Again, it's going to be the voltage drop across my resistor divided by the resistance. This side is at 0. This side is at V in, so we can write 0 volts minus V in over R1. And then for I2, the left side of the resistor is at V in, the right side is at V out, and that whole thing is divided by RF. Okay, so let's go ahead and set these equal. We can say negative V in over R1 is equal to V in minus V out over RF. And we, again, want to solve for V out. So let's go ahead and write this out. I hope I don't run out of room here. V in over RF minus V out over RF. I definitely want to multiply through by RF. And so I'm going to get minus V in over R1 times RF is equal to V in minus V out. And then I get that V out is equal to V in plus V in times RF over R1, or I can factor out a V in, and I get that V out is equal to V in times 1 plus RF over R1. And that is the expression for my non-inverting amplifier topology, okay? So anytime, again, that we have a circuit that looks like this, where I have my my input connected to my plus terminal, my feedback network connected as such, and I don't have my input on the minus terminal, that is the non-inverting amplifier topology, and I can use this equation to determine my output. And so again, in the next video, we're going to go ahead and solve a circuit where we throw in some values, determine V out using this method here, And then once we do that, we'll compare the result to this expression here and show that they are equal. So let's go ahead and end this video right here.